Figure 1 shows a cyclist riding along a flat road. Complete the sentence. Choose answers from the box. As the cyclist accelerates, the something energy store in the cyclist's body decreases and the something energy of the cyclist increases. For this question, it's really important to remember that energy cannot be created or destroyed, only wasted or transferred. We know that the cyclist is getting energy from their body, and that energy is allowing them to move. So, for the first gap, we need to know how the cyclist is getting energy from their body. So let's look at the options. Is it chemical? Well, yes, because there are chemical reactions occurring inside the cyclist's body, and that is giving them energy. So our first answer is chemical. So we can cross that off. For the second box, we know that this is going to be movement energy. Is it elastic potential? Well, elastic potential energy would require that something was being stretched or compressed, which isn't what's happening, so we can cross that off. Is it gravitational potential? Well, gravitational potential energy would require that the cyclist was moving upwards, but we know that the cyclist is travelling along a flat road, and so it can't be gravitational potential. Which leaves us with kinetic energy, and we know that it is kinetic energy because kinetic energy is actually the same as movement energy, so we can write that in the second box. For part 2, the mass of the cyclist is 80 kilograms. The speed of the cyclist is 12 meters per second. Calculate the kinetic energy of the cyclist and use the equation kinetic energy equals 0.5 times mass times speed squared. So this is quite a nice question because we're given the equation that we need and all we need to do is substitute in the right values. So first of all, we need to find the mass. Well, that's here. The mass of the cyclist is 80 kilograms. And secondly, we need the speed. And the speed of the cyclist is 12 meters per second. So all we need to do is substitute that into the equation. So kinetic energy equals 0.5 times mass, which we know is 80 kilograms, times speed, which is over here, 12 squared. Don't forget the squared. And if you put that into your calculator, then you'll get an answer of 5,760. We're given the units in the question, so all we need to do is write that value into the answer box. The third part of this question gives us a lot of information which could seem quite daunting, but don't worry, we're going to read through it and then figure out what things we need to sub in, because we're given an equation. When the cyclist uses the brakes, the bicycle slows down. This causes the temperature of the brake pads to increase by 50 degrees Celsius. The mass of the brake pads is 0.040 kilograms, and the specific heat capacity of the material of the brake pads is 480 joules per kilogram degrees Celsius. Calculate the change in thermal energy of the brake pads and use the equation change in thermal energy equals mass times specific heat capacity times temperature change. So again, we're given the equation in the question, which is really nice. So as before, we're just going to find the values that we need for the equation and substitute them in. So the first thing we need is the mass. So we're about to start in the question. So over here, the mass of the brake pads is 0.04 kilograms. Next thing we need is specific heat capacity, which is found here. That's 480 joules per kilogram degrees Celsius. And if you don't know what specific heat capacity is, it is the energy required to raise 1 kilogram of the material by 1 degree Celsius, or the temperature of the material by 1 degree Celsius. Specific always means per kilogram. And finally, we need the temperature change. So the temperature of the brake pads increases by 50 degrees C. It's an increase, so we're going to use the positive value, so 50 degrees C, If it was a decrease, then we would do minus 50 degrees C. So we're just going to substitute those values in. So the change in thermal energy equals mass 0.040 times specific heat capacity 480 times temperature change, so positive 50. And again, put that into your calculator, you'll get 960. We're given the units in the question again, so just write that answer into the answer box. The fourth and final part of this question is a 1 marker and it's multiple choice, so it shouldn't take us too long. How is the internal energy of the particles in the brake pads affected by the increase in temperature? Tick 1 box. So our options are the internal energy has decreased, it's increased, or it is not affected. So let's think about this. If we have an increase in temperature, that means it has more heat, or more heat energy, which we call thermal energy. So if we have more of the thermal energy, then the internal energy has increased because we have more of it, and therefore we would tick the second option, increased. Figure 2 shows how the current through a filament lamp changes after the lamp is switched on. The normal current through the filament lamp is 1.5 amps. For how many seconds is the current through the filament lamp greater than 1.5 amps? Tick 1 box, and you can see our options on the screen. So looking at figure 2, we know that we want to find when the current through the filament lamp is greater than 1.5 amps. So we'll find 1.5 amps on the figure. It's on the y-axis and it's here. And we want to know where the current is greater than this value. So we're looking at all the parts of the graph that are above 1.5 amps. So that is here where I'm highlighting. So for how many seconds is the current through the filament lamp greater than 1.5 amps? Well, we have the time in seconds on the x-axis. We need to know how much each little square is worth and then count the little squares between this point here and this point here. So if we look at the graph, we can see that 2 big squares, so this is one big square, this is another big square, 2 of those is 0.05 seconds, which means 1 is 0.025 seconds. So if we want to find out how much a little square is worth, then we can do that. 1 little square is, well, it's a tenth of 2 big squares. So there are 10 little squares for every 2 big squares. And so it's the value of 2 big squares, so 0.05 seconds, divided by 10, which is 0.005 seconds. You could also do this, so dividing 1 big square by 5, and that would give you the same answer. So now we're just going to count how many little squares there are between the 2 points. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 little squares. You could also do this, count how many big squares there are altogether, and then add on any more little squares, and that would give you the same answer at the end, but we're just going to do little squares. So we've got 16 little squares. We're going to times that by the time that each little square represents, so 0.005 seconds, and that will give us 0.08 seconds. So that's the time between here and here. So taking a look at our options, is that one of the options? Yes, it is. It's the second one here. So we can tick that, and that's our answer. Part 2. Why might the filament inside a lamp melt when the lamp is first switched on? So if we remember from part 1, we had the graph, and it told us that the normal working current for this lamp in particular is 1.5 amps, but at the beginning the current actually went above 1.5 amps. And so this would mean that the filament could potentially melt, because when you have current going through a wire, that actually heats up the wire, and the higher a current goes, the more heat it generates. So if the normal working current for this lamp is 1.5 amps, but it's going above 1.5 amps, then the lamp might not actually be designed to handle currents above 1.5 amps, and so may be more likely to melt because it hasn't been designed to withstand the temperatures that come with the higher currents. And so the answer for this question is that the current goes above 1.5 amps. That's all the question is asking for, because it's a 1-mark question. There's no need to write anything about what I was just saying about higher currents or currents higher than what the filament is designed for, causing it to heat up and melt. You just need to put that the current does go higher than either the normal working current or than 1.5 amps, which is what was given in the question. For the next part, the lamp is connected to a 24-volt power supply. The current through the lamp is 1.5 amps. Calculate the power of the lamp. Use the equation power equals potential difference times current. So in these situations, when they give us the equation, all we need to do is find the values from the equation and substitute them in. So we know that we're finding the power, so there's no rearranging involved, because you can see power is at the start of the equation, and that's what we're finding. So first we need to find the potential difference, and that's here, 24 volts. We know that potential difference and voltage are both measured in volts, and at GCSE they're interchangeable. And we need to multiply that by the current. So the current is 1.5 amps. So all we need to do now is substitute those values in. So P, or power, equals potential difference 24 multiplied by current 1.5. And putting that into your calculator or just doing it in your head gives you 36. We're given the units in the question, so you can just write 36 into the answer box. The final part of this question is another multiple choice question. LED lamps are much more efficient than filament lamps. What does this statement mean? Tick one box. Our options are: LED lamps have a similar power output to filament lamps. LED lamps waste a smaller proportion of the input energy than filament lamps. LED lamps have a higher power input than filament lamps. Or LED lamps waste a larger proportion of the input energy than filament lamps. So the important part of this question is that LED lamps are much more efficient than filament lamps. So what is efficiency? Well, as a calculation, efficiency is the useful output power of a component divided by the total input power. And if you want that as a percentage, then you can multiply it by 100. So if our LED lamp is much more efficient than the filament lamp, then the useful output power is greater, because if you look at this fraction here, in order to make the efficiency greater, we need the value of the useful output power on top of the fraction to be a larger percentage of the value on the bottom of the fraction, the total input power. If there is a higher percentage of useful output power, and so a higher efficiency, then there is a smaller percentage of the power or the energy that is being wasted. So, for example, if the useful output is light for a lamp, then the wasted energy will be wasted as heat or sound sometimes. So there is less energy wasted, or a smaller proportion wasted, which is what is said for the second statement. And so we can tick there.
this. And so we would draw it in a circuit like this up here. You can also add a little plus on the side of the longest line, and that means that the current flows from positive to negative, so it would be coming out of here and into here. However, that's not necessary to get you the marks, but it's just a little thing to know. So next we're looking for how we can combine 1.5 volt cells to give a total potential difference of 4.5 volts. So the thing that I will be looking for here is there a way that we can combine 1.5 volts or add 1.5 volts together a number of times to get 4.5 volts? Because if we can, we know that these are going to be in series. And just another recap, if components are in series, then they will look like this. So we might have a cell here, and then if we had two resistors in series, they would look like this. So they'd be sort of along the same part of the circuit, and if we took out one of these resistors, so say we took out that one, then this would no longer be a complete circuit. Parallel is the other way that you can combine things. So if we had two resistors in parallel, they would look like this. So we'd have one here, and then we would have another down here, so they're kind of stacked on top of each other. And the way you know that it's in parallel is if we took out this one here, we can see that the rest of the circuit is still a complete circuit, and the circuit would still work. It just wouldn't have one of its resistors in it anymore. So, back to this, we know that we can add 1.5 together 3 times to get 4.5, and so it will be in series. So therefore, what we're going to do is we're just going to draw out 3 cells and connect them together with a wire. Sure the wires actually connect. And there's no need to put on the little pluses, but you can if you wish. And that's it, we don't need to label them or anything, but that is how, if all of these were 1.5 volt cells, then the total potential difference provided by these 3 cells together would be 4.5 volts. Part 2. A student built the circuit shown in figure 3 and you can see figure 3 on the screen. Calculate the total resistance of the circuit in figure 3. Use the equation resistance equals potential difference divided by current. So if we look at figure 3, we need to find the potential difference and we need to find the current. We are actually also given a resistance. We're given the resistance of P in this question. However, we're looking for the total resistance of the circuit, and so we won't be looking for that resistance because that doesn't include the resistance of Q, whereas the total resistance will be the resistance of P added to the resistance of Q. So we're looking for the potential difference. So we can find that here. It's measured in volts. Voltage is also measured in volts, and at GCSE, voltage and potential difference can be treated as the same thing. And we're looking for the current in the circuit, and that's measured in amps, and it's here. Now all we need to do is substitute this into our equation. So we have resistance R equals potential difference. So up here, remember, that's 12. And we're dividing that by current. That's over here, 1.6. And if you put that into your calculator, you'll get an answer of 7.5. We're given the units in the question. The units of resistance is ohms. And so we'll just write.
A student wanted to determine the density of a small piece of rock. Describe how the student could measure the volume of the piece of rock. The first thing to note with this question is that it's worth 4 marks. And with longer questions like this, so 4-mark questions, 6-mark questions, there's not so much 4 specific marks that you have to hit in order to get the marks. It's more about producing an answer that would actually give you the correct results in this case, as it's a question about an experiment. So, one thing that you definitely need to know for this question is about a Eureka can. So I'm just going to draw one in the corner. So a Eureka can looks a bit like this. It's a can, obviously, and it has a little spout in it. And basically what happens is you fill this up with liquid to the point just below the spout, or just at the level of the spout. You then drop in the rock in this case, and that displaces the water above the spout, so it comes out the spout, and then you can collect it in a measuring can here. And the volume of the water, of the water in this measuring can is the volume of the rock that you are measuring. So you use this method for irregularly shaped 3D objects, because if we just had a cube, then we could just do length times width times depth for the volume. But because we can't do that because it's irregularly shaped, we're going to use a Eureka can and find the displacement. So our answer would be: take a Eureka can and a measuring cylinder. Fill the Eureka can with water to the level of the spout. Gently place the rock in the water. It's really important that you're gentle and you don't splash the water, as then you could lose some of it. The water level rises and is collected in the measuring cylinder from the spout. The volume of the displaced water, measured with the scale on the measuring cylinder, is equal to the volume of the rock. So that's how a Eureka can works, and that is how we would answer this question. Part 2. The volume of the piece of rock was 18.0 centimetres cubed. The student measured the mass of the piece of rock as 48.6 grams. Calculate the density of the rock in grams per centimetre cubed. Use the equation density equals mass divided by volume. So for this question, we're given the equation, and so all we need to do is find the values in the question and substitute them in. So first of all, what are we finding? We're calculating the density, which is already at the start of the equation, so we don't need to rearrange it, so that's great. For the equation, we need the mass, and the mass of the piece of rock is 48.6 grams, and we need the volume. And the volume that was measured using the method above was 18.0 centimetres cubed. Just as a quick note, it's a really important thing to check the units of the question. We're looking for the units to be grams per centimetre cubed, and that's okay, we don't need to convert anything because the mass is already in grams and the volume is already in centimetres cubed. However, if it had been given in kilograms, then we would need to change it to grams, or if we were being asked for kilograms per metre cubed, then we need to convert everything, but it's okay, we don't need to do that. So instead, all we need to do is substitute our values in. So, density equals the mass, 48.6 grams, divided by the volume, 18.0 centimetres cubed. And if you put that into your calculator, you'll get an answer of 2.7. We're going to put 2.70 as both of our values up here are 3 significant figures. So we want to give our answer to the same number of significant figures. However, answering with just 2.7 without the O on the end wouldn't lose you any marks. It's just something to note. So we can put the answer of 2.70 into the answer box. For part 3, figure 4 shows the densities of different types of rock. So you can see here we've got basalt, flint, granite, limestone and sandstone, and we're told their densities in grams per centimetre cubed, which is the units that we had earlier in the question. What is the most likely type of rock that the student had? Tick one box. And again, we've got the 5 rocks that I just said. So if you'll remember from the last question, our answer was 2.70 grams per centimetre cubed for the density of the rock that the student had. So we want to find which of these is closest to 2.70, and that is most likely to be the rock that the student had. So the easiest way to do this is just to draw a line from 2.7 here. So if we just draw a line across, we can have a look and see which of the bars are closest to this line, and we can quite easily see that it's this one here, which is limestone. So all we need to do now is tick limestone. For the next part, we need to give one source of error that may have occurred when the student measured the volume of the rock. So there are actually a few correct answers to this question, but we're told that we should only be giving one source, and it is really important that you only give one, because if you give 2 or 3 and one of them is wrong, then you won't get the mark even if your other answer is correct. So the answer that I'm going to go with for this is that not all the displaced water is collected in the measuring cylinder. Other correct answers would include that the eye position of the student when using the measuring cylinder was not level with the measurements. The technical term for this is parallax error. So if you're sort of looking down at an angle like this, so if the measuring cylinder is here and your eye is up here and you're looking down at it, then obviously you're not going to get the right measurement. And another correct answer would be that the water level was not at the level of the spout to begin with the Eureka can. Those would all be correct as well. For the final part of the question, how would the error you described in the above part affect the measured volume of the rock? So this question does depend on what you wrote in the last part. So our answer was that not all the displaced water was collected in the measuring cylinder. And so for that answer, that would mean that the volume would be lower. This is because you would collect less water, so the volume of water that you measure would be less, and therefore you would get a lower value for the volume of the rock. However, if you put a different answer, for instance, with the parallax error, so the eye position when using the measuring cylinder was not level with the measurements, then this could actually make it lower or higher depending on whether your eye was below or above the measuring cylinder. And if you'd put that the water level was not at the level of the spout to begin with, then again, you could only have it below really, because otherwise it would pour out of the spout already. And so if it was below, then the displaced water would fill up part of the Eureka can before it poured out of the spout. And so the overall volume would be lower. Or if you filled it up too far and some of it poured into the measuring cylinder beforehand and you didn't empty it, then the volume measured would be higher. So you sort of have to think about what your previous answer was and edit this question to the necessary or the relevant answer for that. But the volume would either be lower or higher, or in some cases you can put both. Americium-241 is an isotope of americium. Which of the isotopes given in Table 1 is not an isotope of americium? The important thing for this question to know is what an isotope of the same element is. Isotopes of the same element, so atoms of the same element, have the same atomic number. The atomic number is the number of protons in an atom's nucleus. The mass number, on the other hand, is the number of protons plus the number of neutrons in the nucleus. If we look in the question, we can see the normal way that we would write the symbol for an element, or an isotope specifically. The number on the top is the mass number, it's the largest number, and the number on the bottom is the atomic number. So, which of the isotopes is not an isotope of americium? Well, it's the one that doesn't have the same number of protons, so it doesn't have the same atomic number. Up here, we can see that americium has 95 protons, so all isotopes of americium, all atoms of americium, have 95 protons, an atomic number of 95. So looking down here, we can see that B does not have an atomic number of 95, whereas the other two isotopes do. And for that reason, the answer is B. The question also asks for a reason for our answer, and so the reason is that americium has an atomic number of 95. Other valid answers, which are basically different ways of saying the same thing, would be that B has an atomic number of 94, or that B does not have the same atomic number as americium. Figure 5 shows how the number of americium-241 nuclei in a sample changes with time. You can see figure 5 on the screen now. How many years does it take for the number of americium-241 nuclei to decrease from 10,000 to 5,000? So on the graph, first of all, we need to find 10,000 and we need to find 5,000. 10,000 is here, it's the y-intercept of the graph, and 5,000 is here. So we need to find whereabouts the line is at 5,000 on the y-axis and what the x-coordinate at that point is. So what we're going to do is draw a line across from 5,000 to there, and then just draw a straight line down. You would use a ruler for this in the exam. So we've got to here. So we can see that every 2 big squares is worth 200 years, which means 1 big square is worth 100, and each little square is worth 20 years. So if we count, we can see that we've got 1.5 little squares between 400 and our point here. And so that's 1.5 times 20, which is 30. And we're just going to add that to the 400, which gives us 430. So it's 430 years. We're also lucky here because we did start with 10,000 nuclei, and so we didn't have to do any subtractions or anything figuring out what the time was at 10,000 because it was 0. So we can write our answer of 430 years. The final part of this question asks, what is the half-life of americium-241? If you remember from the last question, we found out that it takes 430 years for the number of nuclei to fall from 10,000 to 5,000. 5,000 is a half of 10,000. And so the half-life is actually just our answer to the previous question, because it took 430 years for the number of nuclei to halve. Nuclear power can be used to generate electricity through nuclear fission. Figure 6 shows the process of nuclear fission. Complete the sentences. Choose answers from the box. During the process of nuclear fission, a uranium something absorbs a something. Electromagnetic radiation is released in the form of something. So, first of all, just a brief recap of what nuclear fission is. So it's where larger nuclei, so in this case we've got this big uranium-235 nucleus, and it usually is uranium that's used, are split into smaller nuclei. And this happens because they absorb a neutron, which makes them too heavy and so unstable. And so when things become unstable, they want to become stable again. And in this case, they split into 2 daughter nuclei. So that's here and here. So looking back at the sentence that we're looking at, during the process of nuclear fission, a uranium something. Well, as I just said, it's a large nucleus that splits. And so for this, we would answer nucleus. The uranium nucleus absorbs a something. So as I said before, these black dots are neutrons that are absorbed, and so the answer here is neutron. And finally, electromagnetic radiation is released in the form of something. So this isn't really something that you can work out, you just need to know it. But the electromagnetic radiation is released in the form of gamma rays. For the second part of the question, the UK needs at least 25 million kilowatts of electrical power at any time. A nuclear power station has an electrical power output of 2,400,000 kilowatts. Calculate how many nuclear power stations are needed to provide 25 million kilowatts of electrical power. So, the two numbers that we're working with here are 25 million kilowatts and 2,400,000 kilowatts. So, if 25 million kilowatts of electrical power are needed at any time, and each nuclear power station has an output of 2,400,000 kilowatts, the way we'll find out how many nuclear power stations are needed is we're going to divide how much power we need, so 25 million, by how much power each power station can produce at any one time, 2,400,000. Both of these are in kilowatts, so we don't need to worry about the units getting messed up or changing either of the units. We can just leave them as they are. So if you put that in your calculator, 25 million divided by 2,400,000 gives you a fraction of 125 over 12, which is 10.416 recurring. Now we can't have 10.416 recurring power stations. We can't have a fraction of a power station. And so in this case, you would always round up. You can't round down to 10 because 10 wouldn't be enough because our answer is above 10. So you would round up to 11. So write 11 in the answer box. State 2 environmental issues caused by generating electricity using nuclear power stations. So there aren't just two answers to this, there are many, so I'll go through a few. The first two, and the two that I personally would have thought of, would be that the waste is radioactive and that the fuel is non-renewable. However, other answers could include the waste has a long half-life, the waste is toxic, the waste must be buried, and there is a risk of catastrophic accidents. This one, you may have heard of the catastrophe at Chernobyl with the nuclear power station. The UK currently generates a lot of electricity by burning natural gas. This process releases carbon dioxide into the atmosphere. Figure 7 shows how the concentration of carbon dioxide in the atmosphere has changed over the past 115 years. Figure 8 shows how the global temperature has changed over the past 115 years. Give one similarity and one difference between the data in Figure 7 and Figure 8. As you can see, I've just got Figure 7 and Figure 8 up on the screen, so we can look at them side by side. So, for our similarity, we can see that both of these graphs have a positive correlation. So that means that they start lower, so down here, and end up higher. So both of them are going up. So that's what we'll write for our similarity. Both show a positive correlation. Looking back again at the graphs, we're now looking for a difference. So the biggest difference that we can see here is that for the carbon dioxide concentration, we can see that this continues to move upwards, the graph does, whereas for the global temperature increase, actually levels off at the end. And so that would be our difference. The carbon dioxide concentration continues to increase, whereas temperature increase levels off. The plug of an electrical appliance contains a fuse. What is the correct symbol for a fuse? Tick one box. First of all, with this question, while it's not actually essential to the question, I think it is good to know what a fuse is. A fuse is a safety feature of a circuit that is designed to break or blow above a certain current. And as I said, it's a safety feature. It's just designed so that nothing overheats. So the correct circuit symbol for a fuse is the second option here. However, if you were unsure, you could try doing it by process of elimination. So this first one is actually a light dependent resistor. The third is a diode. And the fourth is a thermistor. So if you were unsure, then you could try looking at the other symbols and seeing if you knew any of them or recognised them. And in that case, you would know that the other one that you didn't know was the fuse. The appliance is connected to the mains electrical supply. The mains potential difference is 230 volts. Calculate the energy transferred when 13 coulombs of charge flows through the appliance. Use the equation energy transferred equals charge flow times potential difference. For this question, all we need to do is look at our equation and substitute the values in, as we're already given the equation. There's no need to rearrange anything because we're looking for the energy transferred, which is already at the forefront of the equation. So first of all, we need to find charge flow. So we're told that 13 coulombs of charge flows through the appliance, and we need potential difference. And the mains potential difference is 230 volts. So all we need to do is substitute this in. So energy transferred equals charge flow, 13 coulombs, multiplied by potential difference, 230. And if you put that into your calculator, you'll get an answer of 2,990. We're given the units in the question. The units of energy is joules. So we'll just write 2,990 into the answer box. Figure 9 shows the structure of a fuse. Write down the equation that links charge flow, current, and time. This is one of the equations that you'll have to remember for the exam. So the equation is that charge flow equals current multiplied by time. You may also see this as Q equals IT. And you would actually get the marks for just writing it in symbols, so Q equals IT for this question. But to be safe, I would always recommend writing out the full words because you don't always know whether they will give you the marks for just the letters. The fuse wire melts when 1.52 coulombs of charge flows through the fuse in 0.40 seconds. Calculate the current at which the fuse wire melts. So for this question, we're going to need the equation that we just wrote down for the previous question, which is charge flow equals current times time. So first of all, we're told that we're wanting to calculate the current. So this equation will need rearranging. So if charge flow equals current multiplied by time, then we can divide both sides by time, and that will give us charge flow divided by time equals current. So current equals charge flow divided by time. So now if we look for those values in the question, we need charge flow, which is 1.52 coulombs, and we need time, 0.40 seconds. So if we do 1.52 divided by 0.40, that will give us an answer of 3.8. We're given the units of current in the question. The units of current are amps or amperes. And so we can just write 3.8 in the answer box. For the final part of this question, the mass of the fuse wire is 0.00175 kilograms. The specific latent heat of fusion of the fuse wire is 205,000 joules per kilogram. Calculate the energy needed to melt the fuse wire. Use the physics equations sheet. So the first thing you may be confused about here is, what is the specific latent heat of fusion? Well, specific latent heat is the energy required to change the state of 1 kilogram of a material, but without changing that material's temperature. And by state, I mean from solid to liquid, or from liquid to gas, or gas to liquid, or liquid to solid. The specific latent heat of fusion is the amount of energy required to change the state by melting or freezing when the material is already at its melting point. But again, as I said, it wouldn't change the temperature. So we're told we need to look in the physics equation sheet. So you would get out your physics equation sheet and you would look for an equation that had the specific latent heat, had mass, and had energy. And I'll tell you what that equation is. It is thermal energy for a change of state equals mass times specific latent heat. This can also be written as E equals mL, where E is the thermal energy, m is the mass, and L is the specific latent heat. So all we need to do is substitute our numbers in. So first of all, we need the mass. The mass of the fuse wire is 0.00175 kilograms. And we need the specific latent heat. And the specific latent heat of fusion is 205,000 joules per kilogram. So we're just going to substitute those values in. So mass 0.00175 multiplied by specific latent heat, 205,000 joules per kilogram. And if you put that into your calculator, you'll get an answer of 358.75. And we're just going to round that to 359. This is because these values are both to 3 significant figures. So we're just going to write that answer into the answer box. Figure 10 shows a hot water tank made of copper. Copper has a higher thermal conductivity than most metals. How does the rate of energy transfer through copper compare with the rate of energy transfer through most metals? Tick one box, and our options are higher, lower, or the same. For this question, the most important point is that copper has a higher level of thermal conductivity than most metals. If it has a higher thermal conductivity, that means that it conducts more energy per second. This means that it will have a higher rate of energy transfer, and so we can tick higher. For part 2, the tank is insulated. When the water is hot, the immersion heater switches off. Complete the sentences. Compared to a tank with no insulation, the rate of energy transfer from the water in an insulated tank is blank. This means that the water in the insulated tank stays blank for longer. If the tank has insulation, or it's insulated, that means that it will have a low thermal conductivity. So it doesn't conduct very much energy per second. Therefore, compared to a tank with no insulation, the rate of energy transfer from the water in this tank is low, or lower, because it's not conducting as much energy per second. This means that the water in the insulated tank stays something for longer. Well, if it's not conducting as much of the heat energy away, then it's retaining that heat, and so it stays hot for longer, or hotter. Figure 11 shows how temperature varies with time for water in a tank heated with an immersion heater. Figure 11 is the graph on your screen now. Figure 12 shows how temperature varies with time for water in a tank heated with a solar panel. And figure 12 is on your screen now. The question is asking us to give one advantage and one disadvantage of heating the water using solar panels rather than an immersion heater. Use only information from Figure 11 and Figure 12. So just to make the explanation a bit easier, I've got Figure 11 and Figure 12 on the screen here. Figure 11 is for the immersion heater and Figure 12 is for the solar panels. So first let's find an advantage of using solar panels. So we want to find what's better about the graph in Figure 12 than the graph in Figure 11 in terms of heating things. So in Figure 11 we can see that the temperature of the water, which is on the y-axis, varies quite significantly. So it goes down, then moves back up again, it goes down, moves back up again, and this happens in intervals all the way across the graph. So the temperature is not heating at a constant rate. In Figure 12, the temperature isn't heating at a constant rate either because it's not a straight line. However, it is heated continuously. So we're starting at the bottom and we're continuously moving upwards on the y-axis, which is good. It's an advantage. And so our advantage would be that the water is heated continuously. It doesn't keep dropping up and down. For the disadvantage, we're going to look at the average temperature of both of them. Now, we don't need to do any fancy calculations for this, we can just have a look. So the disadvantage is going to be that the temperature of the water is lower for the most part in Figure 12. You can see that in Figure 11, the temperature of the water keeps moving back up to 58. So that's at the start, it's also here, 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 and here. However, in Figure 12, 58 would be here, and for the most part of the graph, that is beneath 58 to about there. So the disadvantage would be that the temperature of the water is lower, for most of the time that is at least. There are also other answers for the disadvantages. You could have that the water may not be hot enough, which links to the temperature being lower, or that it takes more time to heat the water. And for that one we can see that it's taking more or less 3/4 of an hour to heat up from being at the lowest point to the highest point, whereas on Figure 12 it takes the full time from 9 o'clock to 5 o'clock. So that's about 8 hours to heat up. During one morning, a total of 4,070,000 joules of energy is transferred from the electric immersion heater. 4,030,000 joules of energy are transferred to the water. Calculate the proportion of the total energy transferred to the water. So the question is asking us for the proportion of the total energy transferred to the water. And for that, we need to do a fraction of the total energy. The fraction is going to be the energy that is actually transferred to the water, which is 4,030,000. And we're going to divide that by the total energy transferred from the electric immersion heater in the first place. So we're doing a fraction of the total energy that the water is receiving divided by the energy that the immersion heater is giving it. 4,030,000, which is what the water is getting, divided by 4,070,000, which is what the immersion heater is giving. And if you put that into your calculator, you'll get an answer of 0.99017 and lots of other numbers, and we can just round that to 0.99, and that'll be our proportion. You could also put 99%, and that would be your answer. Next, we're asked to write down the equation that links energy transferred, power, and time. This is an equation that you'll need to have memorised for the exam, and it is power equals energy transferred divided by time. You may also see this as P equals E over T. However, it's always best to write out the full equation with the words, just in case the exam board decides not to accept the letters. The final part of this question: the power output of the immersion heater is 5,000 watts. Calculate the time taken for the immersion heater to transfer 4,070,000 joules of energy and give the unit. So for this, we're going to need our answer to the last question, which was an equation. The answer we gave was power equals energy transferred divided by time. This will need rearranging as we're looking for the time taken. And so I've written it as P equals E over T to make rearranging easier. So first of all, to rearrange this, we're going to times both sides by T, or time. That will give us PT equals E. And then we can divide both sides by P to give us T equals E over P. So time equals energy transferred divided by power. So now all we need to do is find the values. So we know we're looking for the time taken. We want the energy transferred. So we want the immersion heater to transfer 4,070,000 joules of energy. So that will be our value for E. And we want the power. And the power output is 5,000 watts. So if we substitute those values in, 4,070,000 for E, and we're dividing that by 5,000 for P. Putting that into your calculator will give you an answer of 814. So the answer is 814. However, we are also asked for the unit. So because we were using the standard units for power and energy, so watts and joules, we weren't using kilowatts or kilojoules or milliwatts or millijoules, we can just use the standard unit for time, which is seconds. You could, if you wanted to, also convert this into minutes, so that would give you 13.57 minutes. However, there's no need to do this. 814 seconds will get you all 4 marks, and so it's not necessary to go to the trouble of converting that into minutes. Figure 13 shows a lift inside a building. The motor in the lift does 120,000 joules of work in 8.0 seconds. Calculate the power output of the motor in the lift. Use the equation power output equals work done divided by time. For this question, all we need to do is substitute the values in the question into the equation. So we're calculating the power output, which is already at the front of the equation, so we don't need to do any rearranging, which is great. We need to find the work done. So the motor in the lift does 120,000 joules of work, and we need to find the time that it does it in, and it's in 8.0 seconds. You may notice that work done has the same units as energy, it's joules, and that's because work done is the same as the amount of energy that's been expended, if you like, or that's gone into doing whatever has been done. So we're just going to substitute those values into the equation. So power output equals work done, 120,000 joules, divided by time, 8.0 seconds. And if you put that into your calculator, you'll get an answer of 15,000. The units in the question are watts, which is great because that's the units that we want. And so we'll just write 15,000 into the answer box. We don't need to worry about changing the units or anything because we haven't got kilojoules or millijoules or anything, or milliseconds. We've just got joules and seconds, so that's great. We can just go straight to watts. The power input to the motor is greater than the power output. Tick 2 reasons why. So our options are the energy is transferred in heating the surroundings. Friction causes energy to be transferred in non-useful ways. The motor is connected to the mains electricity supply. The motor is more than 100% efficient. And there are only 4 people in the lift. So let's try this with process of elimination. So the first one that would stand out to me as being untrue is this one here, that the motor is more than 100% efficient. If it was more than 100% efficient, then the power output would be greater than the power input. But we're told that the power input is greater than the power output, so that can't be true. So we can put a little X there, we know it's not that one. Next, with there are only 4 people in the lift. Well, this wouldn't change anything. We could have 5 people in the lift, we could have 2 people in the lift, we could have no people in the lift. That wouldn't change the fact that the power input to the motor is greater than the power output. The number of people in the lift doesn't matter. And so it can't be that one. The motor is connected to the mains electricity supply. Well, again, this wouldn't really change anything whether or not it's connected to the mains electricity supply. This doesn't have anything to do with the power input being greater than the power output, so it's not that one. So that leaves us with 2, and we're asked to tick 2 reasons why. And the reasons that these are true is, first of all, the friction causes energy to be transferred in non-useful ways. Well, that's true because friction causes heat to be produced, if you like, and also possibly light if there's any sparks, and that is wasting energy. So the power input, some of the power input is used up in that energy, and so that is true because we don't want it to heat up or light up anything, and so it's non-useful, but it still happens. And energy is transferred in heating the surroundings. Well, this is one of the things that the friction does. It heats the surroundings up, and that is a non-useful way that the power input is being used. And so that's also true, because the power output is the power being used for what we actually want it to be used for, or the energy that's actually lifting the lift up. Figure 14 shows part of the circuit that operates the lift motor. The lift can be operated using either of the 2 switches. Explain why. First of all, our 2 switches are here and here, so that's what we're looking at. We can see that these 2 switches are in parallel, and just a brief explanation of what parallel means. If we have 2 components in parallel, then let me draw a little diagram. So we've got our cell here, and let's say we have 2 resistors in parallel. So we would have one resistor here. The circuit symbol for a resistor is just a rectangle like that. And to put them in parallel, they're sort of stacked on top of each other, so another here. And if you want to check that something is in parallel, then you could remove one of them. So let's say we remove this one. And this is still a complete circuit. The current can still flow around this circuit. There are no gaps in it. Likewise, if we were to remove the other resistor, this is also still a complete circuit. The current would go down here, through the resistor, and back up. So we can do the same with our 2 switches. So first of all, let's say that we switch this one on. So now this switch is on. So this switch here is open, and so we might as well just remove the entirety of this here, because the current can't flow through it if it's open. But now we can see that we have a complete circuit. The current can flow around here and through. So that means that the circuit works and the lift will operate. Now, if we open this switch and close the other one, now this switch is open, and so that part of the circuit wouldn't work, and so we can actually just get rid of it. But it's still a complete circuit. The current can flow around here, and it would go down and around and back up again. So the circuit is still complete, even though the other switch is open or even just completely not there like we've done. So our answer for this would be that the switches are in parallel. That's your first mark. And so closing either switch completes the circuit. And just to break that down for you in terms of marks, your first mark is here, the switches are in parallel, and your second mark is closing either switch completes the circuit. Next, we're told to write down the equation that links gravitational field strength, gravitational potential energy, height, and mass. This is an equation that you need to remember for the exam. It won't be on your formula sheet. So the equation is gravitational potential energy equals mass times gravitational field strength times height. And as I said, that's just an equation that you'll need to know for the exam. You may also see it written as EP, so the P is in subscript, which means gravitational potential energy, equals mgh, or just E equals mgh. And you could write it like this and still get the marks in this case. However, it's always safer to write it in the words as given in the question, just in case they're being particularly harsh. For the final part of this question, the lift goes up 14 metres. The total mass of the people in the lift is 280 kilograms. Gravitational field strength equals 9.8 newtons per kilogram. Calculate the increase in gravitational potential energy of the people in the lift. Give your answer to two significant figures. So for this, we're going to use the equation that we just wrote down for the previous part, which was gravitational potential energy equals mass times gravitational field strength times height. So we just need to sub in the values. So first of all, we're finding the increase in gravitational potential energy. That's great. That's already at the start of the equation. And so we don't need to rearrange it. Second of all, we need the mass. So the total mass of the people in the lift is 280 kilograms. In this case, we don't need to worry about the mass of the lift because we're finding the increase in gravitational potential energy of the people in the lift. So just the people. So all we need is the mass of the people. We want the gravitational field strength, which is 9.8 newtons per kilogram. You may also see this written as 9.8 meters per second squared. And finally, we want the height, and the lift goes up 14 meters. And so when it says height, it means change in height. So we've gained 14 meters in height. And if we were going down, then we would actually put the height as a negative and we would be losing gravitational potential energy. Because gravitational potential energy is to do with how far you can fall, basically. And so if it was going down, then you would lose gravitational potential energy, and so it would be negative and you'd have a negative height. But because we've moved up, we're going to use a positive value for it. So if we sub in those values, so gravitational potential energy equals the mass, 280 kilograms, multiplied by the gravitational field strength, 9.8 newtons per kilogram, multiplied by the height, or the change in height, which is positive 14 meters. Putting that into your calculator, you'll be given an answer of 38,416. But don't forget, we're told to give our answer to two significant figures. So we're going to round that. Our second significant figure is the 8 here. We've got 4, so that's below 5, and so we're rounding down. So to two significant figures, we would just give 38,000. We're given the units in the question. The units of energy is joules, so the units of gravitational potential energy is also joules. And so we can write 38,000 in the answer box.
Figure 1 shows a student walking on a carpet. The student becomes negatively charged because of the friction between his socks and the carpet. Explain why the friction causes the student to become charged. So this is 2 marks. We need to have 2 really clear points about why the student becomes negatively charged. So we need to understand that in order for them to become negatively charged, there needs to be a transfer of electrons. This is because electrons are negatively charged. We also need to understand for our second point that this transfer happens from the carpet to the boy. Before this transfer, the boy was neutral. He had no charge because we know that atoms are neutrally charged. However, after this transfer, the electrons have been rubbed off from the carpet to the boy. So our first mark is saying that there is a transfer of electrons, and our second mark is saying that this occurs from the carpet to the boy. The student's head is represented by the sphere in figure 2. The student is negatively charged. The arrows show part of the electric field around the student's head. Draw 3 more arrows on figure 2 to complete the electric field pattern. So, the first thing that we need to understand when drawing an electric field is that if the field around the object is the same, which we're assuming it is in this question, the lines need to be equally spaced out. If we drew them and they weren't equally spaced out, this would indicate that there is a change in the strength of the field. However, in this case, the field is the same all around the object. Therefore, to draw 3 more arrows, we want them to be equally spaced out around the body, like so, and so they're perpendicular. Then we need to think about what direction does the arrow go in. So when we're looking at electrical field patterns, what we're describing is what would the path of a positively charged particle be in this field. So we know that due to electrostatic attraction, negatively charged particles and objects are attracted to positive charged particles. So this particle would move towards the body. Therefore, we draw the arrows inwards, like so, pointing towards the body. Also, the fact that the line that is drawn at the top that they've already given us, the fact that that is pointing inwards does also indicate to us that the other 3 lines on the body will point inwards, but it's just really good to understand why this is. The negatively charged student touches a metal tap and receives an electric shock. Explain why. So this is an explain question. That means we need to add more detail than if it was a state or a describe question. So firstly, we've got this negatively charged student who's touching a metal tap. And we need to understand that this tap is earthed, so it is at 0 volts. It is also a conductor, as metals are conductors. So we have the metal tap, which is at 0 volts, and we have the negatively charged student. They have a buildup of electrons on them. This means that they are not at 0 volts. Therefore, there is a potential difference between the negatively charged student and the metal tap. So we know that when we have a potential difference, this allows a current to flow. And this current is the flow of electrons from the negatively charged student to the tap, which conducts these electrons. And for our final point, we need to mention that this means that the charge has been earthed. This means that the charge has moved from this negatively charged body, the student, to the earth. So the student has been discharged, or their negative charge has been gotten rid of. Some carpets have thin copper wires running through them. The student is less likely to receive an electric shock after walking on this type of carpet. So, copper is a good conductor. Therefore, what's going to happen is instead of the electrons flowing from the carpet to the student, it's going to flow through the copper wires instead. Because there is less electrons flowing through the student, this means that the potential difference between the student and the carpet is less. We know that potential difference allows a current to flow, therefore there's a smaller potential difference. It will not be large enough for a current to flow. Therefore, they will not receive an electric shock. A teacher uses a Geiger-Müller tube and counter to measure the number of counts in 60 seconds for radioactive rock. The counter recorded 819 counts in 60 seconds. The background radiation count rate was 0.3 counts per second. Calculate the count rate for the rock. So when we're asked to calculate the count rate, what we need to calculate is the counts per second. And what they've given us here is the data 819 counts in 60 seconds. Therefore, if you want to calculate the number of counts per second, we need to do 819 divided by 60. Now this gives us 13.65 counts per second. And they've also given us the background radiation count rate. So we use this piece of data and we minus this from 13.65. And we do this because the overall count rate that we've recorded is 819 counts per 60 seconds. This includes both the count rate from the radioactive rock and the background radiation. Therefore, what we need to do is minus 0.3. So 13.65 minus 0.3. That gives us 13.35 counts per second, like so. A householder is worried about the radiation emitted by the granite worktop in his kitchen. 1 kilogram of granite has an activity of 1,250 becquerels. The kitchen worktop has a mass of 180 kilograms. Calculate the activity of the kitchen worktop in becquerels. So, BQ, becquerels, is a unit of the activity of a radioactive source. So they've told us that for 1 kilogram of granite of this material, the count rate is 1,250 becquerels, BQ. Therefore, this man has 180 kilograms, what we've done to get from here to here, multiplied by 180. So we're going to do the same because the count rate will also increase by the number of times that the mass is increased. So times this by 180, we do 1,250 multiplied by 180, and we get 225,000 becquerels. The average total radiation dose per year in the UK is 2 millisieverts. Table 1 shows the effects of radiation dose on the human body. So here we're given a table with radiation doses in millisieverts, and on the right with the effect that they have. As the radiation dose increases, the effects get worse and worse. The average radiation dose from the granite workshop is 0.03 millisieverts per day. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop. 1 year is 365 days. So we're asked to explain why they don't need to be concerned about the yearly radiation dose, but notice we're only given the dose from the worktop per day. So in this question we need to first calculate the dose that the user will get per year, and then because it's an explain question for the second mark, we then need to say why this value that we've calculated means that they don't need to be concerned. So to calculate the yearly radiation dose received from the worktop, we do 0.003, which is the daily dose, multiplied by 365, the number of days in a year, and we get 1.095 millisieverts, which is little m and then SV. So then for our second mark in this explain question, we need to say, why does this mean that the householder does not need to be concerned? So if we look up to the table again, we can see that 100 millisieverts is the lowest dose with evidence of causing cancer. And what we can notice about the value that we've calculated is this is significantly less than this value, which even hints at causing some serious illness. Therefore, we need to say that the value we've calculated, the yearly dose, is significantly less than the smallest amount required to cause serious harm. Bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. Suggest one reason why the banana equivalent dose may help the public be more aware of radiation risks. So this is a 1-mark question, we just need one reason suggesting why it could be helpful to people to change the units of radiation dose from sieverts to banana equivalent dose. And what we need to get at here is that the banana equivalent dose is much more relatable for people. It's a lot more simple to understand a radiation dose in terms of a banana, which is kind of understandable and in everyday life, in comparison to sieverts, which a lot of people wouldn't understand what this means in context. So yeah, it's easier to compare the banana equivalent dose to something that people are aware of in everyday life, whereas sieverts is more difficult for people to understand. A student investigates how the resistance of a piece of nichrome wire varies with length. Figure 3 shows part of the circuit that the student used. Complete figure 3 by adding an ammeter and a voltmeter. Use the correct circuit symbols. So this is a 3-mark question. We're going to get the first mark for using the correct symbols for an ammeter and a voltmeter, and then 2 more marks for putting those in the correct place in the circuit. So if we look at the experiment that we're doing, we're changing the length of this nichrome wire here and seeing how does this affect its resistance. So we need to understand that resistance R equals V over I, voltage divided by current. Therefore we need a voltmeter in order to measure the voltage, and we need an ammeter to measure the current. So that's why we need those 2 components in this circuit that they've given us. So the symbol for an ammeter is just an A in a circle like so, and then the symbol for a voltmeter is AV in a circle like so. So when we're talking about current, we talk about the current through a component. And what we need to do to calculate the current through this wire that they've given us is just put the ammeter in series. So in series just means at any point along this wire would be in series with the nichrome wire. So for example, I could put it here, just draw an A, this is my circuit symbol. But for example, it could also go here, it could go here, it could go anywhere on this circuit, and that would still be a correct answer. And now for the voltmeter. When we're talking about voltage, we talk about, or potential difference, we talk about the potential difference across a component. So when we're talking about potential difference, we're talking about the potential difference between 2 points. For example, these 2 points on either side of the wire. We're talking about the difference in energy transferred per unit charge from this point to this point. So we need to put our voltmeter in parallel with our component. So that looks like this. Describe how the student would obtain the data needed for the investigation. Your answer should include a risk assessment for one hazard in the investigation, and this is a 6-mark question. So you might get 1 or 2 of these 6-mark questions in your exam paper asking you to describe a practical. So what we need for this 6-mark question is to clearly answer the question, which is how would we obtain the data, And this also needs to be written out very clearly and in a logical way in order to get those full 6 marks. So first, just to provide some understanding of the practical. What we're doing is we are changing the length of the wire and we want to see how this affects the resistance. So if we were to draw a graph, we would have length on the x-axis, that's measured in meters, and then we would have resistance on the y-axis, and that is measured in ohms. So as we change the length, which is our independent variable, is what we are changing and seeing its effect on the dependent variable, which is resistance. We're measuring this to see how it changes. So what we need to do is talk about how we obtain the data, which allows us effectively to draw this graph. So what we need to notice is that resistance R, as mentioned in the first part of this question, equals V over I, because what we're measuring is the voltage and the current. So we need to discuss, firstly, how we take the voltage measurements, how we take the current readings, and then how we use these to find the resistance of the wire at each length. We also need to discuss what apparatus we use at each stage in order to make the measurements. So then we need to talk about the how we can improve the accuracy of our investigation. And most often we do this by taking repeat readings. What we do is, for example, with this, we would unplug the circuit, we would take, we then plug it back in, we would take a current reading and we would take a voltage reading. Then unplug the circuit, take another current reading and another voltage reading. Then unplug it, plug it in again, take another voltage and a current reading. We would then have 3 readings, 3 current readings, 3 voltage readings. As long as none of these were anomalous results, we would then take a mean or an average of these results and then use this to calculate the resistance. This just allows us to remove any anomalies and give us a more accurate result. Then we need to look at the part of the question where they ask us to include a risk assessment for one hazard. So when they ask for a risk assessment, they want us to identify the hazard. We need to identify the risks that this could cause and then identify how we are going to avoid it. A risk in this experiment is that the wire could overheat, and this could happen if we use very large currents. So what could happen if we allow this to take place is that the person doing the experiment could get burnt, which is a risk. And then how we're going to avoid this happening is by using a low current throughout the experiment. After we've taken repeat readings for both the current and the voltage, and then calculated a resistance for each length of wire, we then need to plot resistance against length. Why would switching off the circuit between readings have improved the accuracy of the student's investigation? Tick 1 box. This is a 1-mark question, we just need to select one of the answers. So in this experiment, we are calculating how the resistance of our wire changes according to how we change length. So that means we have 2 of these variables, the independent variable and the dependent variable. Along with this, we also have control variables. These are things that we need to keep the same in order for us to be able to fully see how length affects resistance. So one of these is the temperature of the wire. And we need to control this because when the temperature of the wire increases, this causes an increase in resistance. So what we need to do is to try and control this temperature, to try and keep the temperature of the wire constant throughout our experiment. So the way we can do this is by switching the circuit off between readings. This is because when we switch the circuit off, this causes the current to stop and gives the wire a chance to cool down. therefore controlling temperature. Therefore, the answer that most correctly describes why we disconnect the wires between readings is the last answer. The temperature of the wire would not change if we disconnected the wires. The student uses crocodile clips to make connections to the wire. They could have used a piece of equipment called a jockey. Figure 4 shows a crocodile clip and a jockey in contact with a wire. How could using the jockey have affected the accuracy and resolution of the student's results compared to using the crocodile clips? So in order to answer this question, I think first it would be good to understand the definition of both accuracy and resolution. So accuracy is how close is the value that we've measured to the true value. And the resolution of the measurement is what's the smallest change, for example, in this experiment with length, that I could measure using this equipment. So when we're looking at accuracy, which is the first 3 options of this question, we're given the choices that accuracy would be higher, that accuracy would be lower, and that accuracy would be the same. So let's look at what we have here. So the accuracy is how close is my value to the true length of the wire. Now we can say that the jockey, so the second measurement, that's going to give a value closer to the true length of the wire, because you can see that the tip here of this measuring device is much smaller than the crocodile clip. This gives us a much more accurate reading, which means a reading that's closer to the true value. Therefore, we can say the result is more accurate. Then looking at resolution, so the smallest change in length that could be measured. If we think about the resolution with the crocodile clip, the resolution is lower for this way of measuring the length. And this is because, again, we have a wider base, and therefore the ability to change the length and measure this is reduced. Therefore, with the jockey, we have an increased resolution. Therefore, it is this option. The resolution of the length measurement would be higher.